Hi, everybody. Thank you for joining me for this lecture, Lecture 3. We're going to be doing more descriptive statistics today. We're going to be covering frequency distribution tables and histograms. A frequency distribution table is a statistical tool used to organize and summarize a set of data by showing how often each value or range of values occurs within a data set. It groups in data into categories, and we call the categories classes. Sometimes we'll call them intervals. It lists the number of occurrences for each category, and the number of occurrences we refer to as the frequency. Let's say a study collects the ages of 50 people, and the data is grouped into 6-year intervals. This is what a frequency distribution table, when it's completed, this is what it looks like. We have columns for classes. In this example, the classes represent age range, and we have a column for class boundaries, class mark, frequency, and relative frequency. So I'm going to first start talking about the first column. After I completely explain the frequency distribution table, we are going to build one from scratch. So the first column, called classes, are ranges into which the data is grouped. Now, we are going to be building frequency distribution tables from numerical data, so we will not be doing this with categorical values, although it can be done with categorical variables. Each class has a lower class limit and an upper class limit. The first number in the interval is the lower class limit, and the second number is the upper class limit. So here we have a lower class limit of 10 and an upper class limit of 15. And there are 5 classes in this example, and that refers to the rows: first class, second class, third class, fourth class, and fifth class. The classes are all equal in size. 10 to 15 has the same size as 16 to 21, which has the same size as 22 to 27. The size in a frequency distribution table is called the class width. What is the class width in this example? So if we look at 10 to 15 and 16 to 21 and 22 to 27, many students are tempted to say that the class width is 5 because they take the difference. But it turns out that the class width here is actually 6. And you can calculate it by subtracting 2 consecutive lower class limits or consecutive upper class limits. So for example, if you take 16 minus 10, you get 6. If you take 21 minus 15, you get 6. And the reason why the class width is 6 is because if you list all the values from the lower class limit to the upper class limit, so 10, 11, 12, 13, 14, 15, and count them, 1, 2, 3, 4, 5, 6. It spans 6 values. So the class width is 6. Now that's true for every one of these classes, because if you were to list all the numbers from 16 to 21 or 22 to 27, you would also have 6 values. So the quick way to do it is to just subtract consecutive class limits. So for example, 34 minus 28 will give you 6 as well. Okay, so I want to show you some mathematical examples of finding the class width by using that first column. I want to reiterate, though, that the class width is the same throughout. It's consistent throughout the entire table, no matter which 2 consecutive lower class limits or upper class limits are subtracted. So here's an example. I'm sorry, let me go back. So here's another example. If we do 39 minus 33, it's 6. Class width is 6. If we do 22 minus 16. The class width, sorry, the class width is 6. So we see 6 over and over again here. Different problems will have different class widths. It will very rarely always be 6 in the problems that you encounter here. So be prepared for class widths to take on different values, but in this particular one, in this particular frequency distribution table, the class width is 6. The other thing that could be variable that I didn't mention is the number of rows, which are the number of classes. We have 5 classes in this example, but another example could have more. So you can have variable size frequency distribution tables. The next column, called class boundaries, are the actual upper and lower limits of the intervals, which is used when the data is continuous. So note that the classes column, these values, 15 and then following 15, the number 16, those are discrete quantities. And look, 21 to 22. That's a discrete jump. It's a gap between those two values. Whereas class boundaries, there is no gap. If you take note of what we have here, the upper class boundary or the upper class limit of the first class boundary is the same as the lower class limit of the next class boundary. So there is no gap between the class boundaries. And the way we arrive at the numbers in this column is by subtracting 1/2 from the lower class limit and adding 1/2 to the upper class limit. So 9.5 is 10 minus 0.5, and 15.5 is 15 plus 0.5. 16 minus 0.5 is 15.5. 21 plus 0.5 is 21.5, etc. And we're doing this so there are no gaps between the intervals. Okay, and there's mathematically how we calculate the class boundaries for the first class, and the subsequent classes will be calculated in the same way. Class marks are the values that are halfway between the upper and lower class limits of each class, so the midway point. You can find the class mark by taking the average of the upper and lower class limits. So let's look at the first example. The first class has lower class limit 10 and upper class limit 15. And taking the average would mean we'd add them up and divide by 2. So adding up 10 plus 15 and dividing by 2 gives us 12.5. I do want to share with you the calculator approach for doing this calculation because the parentheses are really important there, and I want to make sure you include them. So let me just share the calculator. Hold on a sec. So here's the calculator, and I'm going to do the calculation 10 plus 15 divided by 2. Using the parentheses key here, I'll do 10 plus 15, close the parentheses, and then divide by 2. And I get 12.5 just like the slideshow shows, but I want to show you the incorrect way of doing this without the parentheses. Gives 17.5. And the reason why these numbers are different is without the parentheses, 15 divided by 2 is being calculated first, then that answer is being added to 10, whereas in the correct approach with the parentheses, 10 plus 15 is evaluated first, and then that answer is divided by 2. So when you do these examples, you have to make sure you include the parentheses. Okay, so let's take a look. If we were to do the same calculation on the second class, 16 to 21, we would add 16 plus 21 and divide by 2, and that gives us 18.5. And we would continue in the same way for all the class marks. However, there is a shortcut. After you find the first class mark, there is a relationship between um, between one row and the next. And if you can spot it, it'll look familiar to you because every subsequent row is 6 more than the previous. And that is the class width appearing all over again. So the class width appears frequently throughout this table, and when it's calculated correctly, it helps to structure the table, and it will never be different. It will always be the same here. The class width will always be 6 here in this example. It will always be 6 here. If you do 15.5 minus 9.5, you do get the class width of 6, and it's 6 here. The difference between one class mark and the following class mark is also 6. So that would be a shortcut to evaluating that column of class marks. Okay, next, let's look at frequencies. In order to calculate frequencies, you need to be looking at the raw data that a problem provides you. Now, in this example, we are not provided with raw data that was used to build this frequency distribution table. But the table tells you that there were 5 items in the raw data that fit between 10 and 15. Since this is about ages, it means that there are 5 people in the sample whose ages are between 10 and 15. And the 8 means there's 8 people in the sample whose ages are between 16 and 21. And let's take a look at the highest frequency here. 15 people in the sample with ages between 28 and 33. Okay, so frequency, it's the number of data values that fall within each class interval. This table is organizing 50 people into age ranges. There are 5 people with the ages between 10 and 15, 8 people with ages between 16 and 21, etc. There's a relationship between the total frequency and the sample size. If we add up all the frequencies, it should sum to the sample size. And if it doesn't, it probably means we have a calculation incorrect in our table. If we add up 5 plus 8 plus 12 plus 15 plus 10, it equals 50. It equals 50, which is the size of the sample. So we have that matching, and it should always equal the size of the sample. Okay, so if you're building a frequency distribution table and you want to validate that the frequency column is correct, you can add up each frequency and ensure that it sums up to the size of the sample. Okay, relative frequency is the proportion of data values in each class expressed as a percentage of the total. All this means is that we are taking the frequency and converting it into a percent. So this 5 is, remember that this is out of a total of 50. So this 5 is 10% of the total. And this 8 is 16% of the total. To calculate that, just take this is a division problem. You're going to take 5 divided by 50, get your proportion, and then convert it into a percent by multiplying by 100. So that's where the 10% is coming from. 5 divided by 50 times 100. And then in the next one, 8 divided by 50 times 100. When you're doing this on your homework, you may have numbers that don't round nicely. Maybe they don't terminate when you're calculating the divisions. If that's the case, when you convert it to a relative frequency, or when you convert it to a percent, you may have to round it, and the rule will be round to 2 decimal places if you need to. That's 2 places after the decimal point if it's necessary. Now, in this case, none of that was necessary because we're dividing by 50, a nice even number, and we're going to get these nice whole number answers. But if you don't have a whole number answer, round to 2 places after the decimal point. There's a relationship between the relative frequencies, and I guess I don't have it in the slideshow, but you should recognize that the sum of all these percentages should equal 100%. Okay, and if they don't equal 100%, you may have done something incorrect. If you end up needing to round your relative frequencies, then it's possible that it may not exactly be 100%. It may be 99.99% or 100.01%. And that's okay because that's a rounding error, but you shouldn't be off by more than that. So we're going to build this step by step. I'm going to give some context to this problem. The scenario is a medical study collects the systolic blood pressure readings for 50 patients to analyze the distribution and identify patients who are at risk for hypertension. The systolic blood pressure readings values range from 100 mmHg to 196 mmHg. The goal is to group these readings into categories to better understand the spread of blood pressure levels in the population. So we are told that we're going to build a frequency distribution table, and we're told there are going to be 5 classes. This means that there will be 5 rows. So different problems will have different requirements. This one says 5 classes. We're going to put data into our calculator first. This is step 1. So we're going to find an empty calculator list, and we're going to put the numbers in, and once they're in, we're going to sort the list. So if you remember from the last lecture, I showed you how to put data into a calculator, but I am going to do it again here. If you want, you could pause the video and put these numbers in on your own, or you can follow along with me, and I'll do it in the calculator here. Okay, to get to our calculator list, we're going to press Stat and then Edit. So we hit Enter when Edit is selected. This list 1 already has numbers in it. Actually, I put these in already, so I'm going to put them in again. So I'm going to clear out what's currently in L1 and hit Enter. And now I'm going to put those numbers in again. 115, 182, 134, 125, 167, 150, 196, 155, 180, 133, 118, 153, 130, 178, 172, 110, 135, 119, 128, 170, 148, 185, 147, 164, 139, 165, 145, 127, 160, 131, 187, 187. Okay. 142. 120. 152. 157. 122. 100. 115. 190. 136. 159. 105. 168. 132. 162. 175. 140. 144. 137. And now you can see I'm at the 50th value. I'm going to put in the last number, 138. If you made a mistake and you need to replace one of your numbers with another number, I'm going to just pretend that this was supposed to be 130. And I can just hover over it, highlight it, and put the correct number in, and then hit enter, and that new number would take place. Okay, but that's not the case. Let's go back and put that back to 140. If you skipped a number by accident and you want to put another number inside, you can use the insert function, which is in blue above the delete key. Second and delete. Second is going to get access to any of the blue functions above the keys. And you can see it puts in an extra row there. And then you could have the option of putting whatever you want in that other number. So if it's now I want to delete this because it's not supposed to be there. If I put my cursor on it, I could press delete and it goes away. So with all of these in the calculator, we're going to sort them in ascending order. So stat, stat, now go down to number 2. We're going to sort list 1, so we want to activate the L1 above the number 1 down here. Second, L1. Close the parentheses. Now the calculator is sorted. If we go back into that list, stat, edit, the numbers are in ascending order. Now, I want us to take note of the smallest and largest, and then we're going to go back to the slideshow. So the smallest here is 100, and if we go up and up again, it brings us down to the bottom, and the largest is 196. In building a frequency distribution table, you need to know those values, smallest and largest. So here, 100 and 196. And now I'm going to go back to the slideshow. So now that we've put the data into the calculator's list, the next step is to calculate the class width. So with the data on your calculator, you've taken note of the smallest value and the largest value. So those two numbers, 100 and 196, allow us to compute the range of our data. So we take the largest value, and that's the 196, and we subtract the smallest value, that's 100, and that gives us a range of 96. Each problem is going to provide you the number of classes that are required. So here the number of classes was 5. We take our range and we divide it by the number of classes. And then we go up to the next whole number. So this is the first time in this class, actually it's the only time in this class that we are going to not follow normal rounding rules, and we're going to go up to the next whole number regardless of anything that occurs after the decimal point. When we take 96 and divide it by 5, the answer is 19.2, but we are going to round that up to 20 regardless of what's after the decimal point. And the reason for making our class width go up to 20 is because if we don't make it big enough, if we make it 19 instead of 20, the class width has to be a whole number. But if we make it 19 instead of 20, the risk is that when we get to the bottom of our list of values, those larger values at the bottom won't have a class to fit into because the class width isn't big enough. So it's important to go up to the next whole number for making sure your data has a place to go when it's placed in the frequency distribution table. The class width is different for different examples. So in this example, it's 20. In the example I showed you before, it was 6. But you always want to make sure to go up to the next whole number. I want to show you another example. Let's suppose hypothetically that the highest value in the calculator was not 196, but it was rather 195. So to calculate the range, you're going to take your largest value minus your smallest value, and you're going to get 95. And then dividing by the number of classes, 95 divided by 5 gives us, and this time it gives us a 19. Now, that's technically like 19.0. The rule is, even though it gives you a whole number answer, you must go up to the next whole number to make that class width big enough. If you don't, those bottom values on the calculator list, the highest values, are going to not have a place to go. So you want to make sure you always round up to that next whole number, even if there's nothing after the decimal point, like in this case, 19.0. Okay, so with your class width established, and we're going to remember that that's 20 here. With the class width established, let's fill out the first column. These are all the classes. Now, this represents systolic blood pressure. So we're going to have a lower limit and an upper limit to each of these classes. And then we usually put a dash in between to indicate that it's an interval of values. So the very first class has a lower limit that is equal to the smallest data value. So since that smallest data value is 100, 100 is the lower class limit. Before we figure out the upper class limit, I'm going to show you a technique that makes things much simpler. We're going to take our class width 20 that we discovered before, and we're going to add it to 100. That's going to give us the lower limit of the second class. That's 120. Then we're going to add the class width 20 to 120, and we're going to get the lower limit of the third class, 140. We'll add 20 again and get the lower limit of the fourth class, 160. We'll add 20 again and get the lower limit of the fifth class, 180. So I just added the class width each time, and I was able to populate all the lower limits of each of these 5 classes. The upper limits, the relationship between a lower limit and an upper limit is if you take a look at the lower limit of the second class, the upper limit of the first class is just 1 less. So subtract 1 and get 119, subtract 1 from the 120 and get 119, and that's the upper limit of the first class. So the first class is complete. It's 100 to 119. The second class, and we're getting there, starts at 120, and you could probably guess that the upper class limit is 1 less than 140. It would be 139. The other way you can also calculate the upper class limit is by adding 20, the class width, to each upper class limit. So starting with 119 and adding 20, you get 139. If you add another 20, you get 159. If you add another 20, you get 179. You add another 20, you get 199. So that 20 as the class width has to be perfect. If that class width was calculated incorrectly in the step prior to step 3, um, this part would completely be incorrect. So you want to make sure that the class width is perfectly calculated before moving on to this step. If you find that you do this for homework and you get a lot of these answers wrong, it may be because your class width was calculated incorrectly. So that may be something to revisit in the event that you get marked wrong on some of these problems. Okay, so with that, with the classes column completed, let's now look at the class boundaries column. These ensure that there is no gap between our classes. And if our data is continuous, this step would make sure each data value belongs in some class. So all we have to do here is take our lower limit and upper limit, subtract a half from the lower, and add a half to the upper. So 100 to 119 becomes 99.5 because you're subtracting a half from 100 to 119.5, adding a half to 119. And you continue this for all classes. So subtract a half from 100, add a half to 119. Subtract a half from 120, add a half to 139.5. Subtract a half from 140, add a half to 159.5, etc. Okay, so we have the classes column complete. We have the class boundaries column complete. Class marks. Class marks, also called the class midpoint, is the average of the upper and lower class limits. So remember, the upper class limit is 119 here, and the lower is 100. If we want to find the class mark, we just take the lower class limit, add the upper class limit, and divide by 2. So 100 plus 119, divide by 2, 109.5. And if you're doing this on the calculator, ensure that you're putting the numerator in parentheses to ensure that it's being calculated first. So I will share the calculator to show you how that works. Okay, so we want to do 100 plus 119 and divide by 2. So if I take it in 2 separate steps, I'll also get the same answer. 100 plus 119 for the first step, get an answer, and then divide by 2, and that's the class mark. Or if you want to do it in one step, put 100 plus 119 in parentheses, and then divide by 2. And you do get a different answer if you fail to put parentheses, like I had shown before. Okay, so it's way off when you forget to use parentheses. So try to make sure to remember to use those parentheses. So you can either use classes or class boundaries to calculate the class mark. So you would get the same answer if you chose to use 99 and 119, 99.5 and 119.5. 99.5 plus 119.5 divided by 2 will also give you 109.5. So we put our class mark 109.5 here. Now you can do that calculation for all the classes, but you do have that relationship, like I described before, that if you add the class width, you can just compute the class mark for the very first class and then just repeatedly add your class width of 20 to subsequent classes, and you could get to subsequent class marks, and you get the next class mark. Okay, so that is a shortcut for calculating that third column. Okay, so I hid the class mark column for a moment because I want space to show you how to calculate the frequency. So classes are the first column. You are going to use this classes column to determine the count or the frequency of data values that are in each class. So for the first column, for the first class, you're going to count how many numbers on the calculator list are in between 100 and 119, and you'll put that number in frequency. Then you're going to count on the calculator list how many numbers are between 120 and 139, and you're going to put that number under frequency. So let's do the first one together. Looking at the numbers that are between 100 and 119, I'm going to share my calculator and we can count that together. So opening up the calculator list, stat, edit, hit enter, and count the numbers between 100 and 119. So I have 1, 2, 3, 4, 5, 6, 7. So it's not between 119 and between 100 and 119 exclusive. It's between 100 and 119 inclusive, meaning that we are including both the 100 and the 119 in the count. So including 100 and 119, we have a frequency of 7. With my calculator open, I could just demonstrate to you how we would do the next class, which is 120 to 139. So let's count the numbers from in between 120 and 139. How many numbers in our list are within that range? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 15. 15 data values fall between 120 and 139, and we'll take note of that on our table. We would continue in that way through the entire list, determining how many numbers fall within the range for each class. Okay, so we have 7 for the first class, and we calculated 15 for the second class, and the rest of the classes are going to be calculated in the same way. So the numbers here are 7, 15, 12, 10, and 6, and that's just what our data gave us. This is going to be unpredictable, and you'll find out when you have raw data that you have to sort what these frequencies will be. The sum of these numbers is supposed to equal the sum of the sample. So if you do that and you add 7 plus 15 plus 12 plus 10 plus 6, you can confirm that all of your frequencies are accounted for, all of your data values are accounted for, and they sum to 50, which is correct. Okay. I wrote here relative percentage. Sometimes it's referred to as a relative percentage. Sometimes it's a relative frequency. They mean the same thing. To calculate the relative frequency, convert this frequency into a percentage. And we're going to do that for all 5 of them. So to convert 7 from a frequency to a percentage, you have to divide it by the total number of data values. So we're dividing by 50 here and then multiplying by 100. So 7 divided by 50 times 100 will give us 14%. If needed, we may get numbers that are non-terminating. And if that's the case, you're going to round your relative frequency to the nearest hundredth, which is 2 places after the decimal point. And continue this for all classes. So if we do the next one, 15, mathematically, we would do this. 15 divided by 50 times 100, and that will give us 30%. 30%. And then 12 divided by 50 times 100 gives us 24%. And if you need, you can use your calculator. 10 divided by 50 times 100 equals 20%. And then the last one, 6 divided by 50 times 100 equals 12%. Okay, and there are our relative frequencies. If we sum them up, they equal 100, and that's how we know we did our work correct. Okay, so a frequency distribution table, once complete, like this one, can be analyzed. And what I've highlighted here is the row of highest frequency. The highest relative frequency of patients, and that's 30%, have blood pressure in the range of 120 to 139 mmHg. This is considered pre-hypertension. And analyzing the table like this can give us some insight into this sample of people. And if we're sampling a particular population, it may give us some indication of the kind of outreach we need to conduct in the population, because it indicates this particular group indicates a need for lifestyle changes to prevent the progression to hypertension. So let's analyze this a little further. The highest blood pressure in the group is a very high risk group. 12% of patients have systolic blood pressure above 180 mmHg, dangerously high. This group requires immediate medical attention to avoid complications. So notice there's nothing higher than 199. So the way this was stated, above 180, just indicates that there is nothing more than 199. Okay, so these are all the values in that top group. Okay, this group, these two groups, when highlighted together, they make up 44%. 44 patients have blood pressures between, and we look at the lower limit of the first of these two classes, and we look at the upper limit of the second of these two classes. So we say that 44 patients have blood pressures between 140 and 179. Indicate a significant portion of the population is hypertensive, requiring ongoing medical monitoring and possible treatment. So if you have multiple rows, multiple classes that you're accounting for, realize that the frequency is the sum of the two frequencies for that class, for those classes. Okay, so that completes the frequency distribution table. It's very much tied to the next topic that we're going to talk about, which are histograms. Histograms take this numerical chart, a frequency distribution table, which is very number oriented, and converts it into something that's more visual and more obvious to see changes and see anything that's striking, because it will stand out to you. So this is a histogram. And so the visual nature of it is very similar to a bar graph. It's a graphical representation of a frequency distribution table where each bar represents a class interval. The horizontal axis, right here, is a number line with the variable the data represents. In this case, it represents heights. And it doesn't tell you the scale here, but it is in inches. So these numbers here are in inches. The horizontal axis is the variable, but the vertical axis is either going to be relative frequency, as shown here, or sometimes it is the frequency. It depends on the graph. And it is the height of each bar corresponds to the frequency or relative frequency of data values within that class interval. So what you see here is the highest bar corresponding to the highest frequency or relative frequency. The lowest bar corresponds to the lowest relative frequency. Let's keep going with this. There are 8 boxes or classes. So in this case, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 classes. Sorry, let me get that back. There are 8 classes, and you can see them here, 1, 2, 3, 4, 5, 6, 7, 8. And that would mean that in a corresponding frequency distribution table, there would be 8 rows, 8 classes. The first class has a relative frequency of 5%. 0.05 is 5%. The second class has a relative frequency of 3%, etc. The horizontal axis corresponds to the class boundaries of a frequency distribution table. So see here, 59.5 and 61.5, that would be the first class, and those numbers are the lower and upper class limits of the first class. The second class, 61.5 to 63.5, those are the lower and upper limits of the second class. And the third class, 63.5 to 65.5, the lower and upper limits of the third class. And this goes on for the rest of the table. The width of each rectangle or each box, the width is found by subtracting upper class limit minus lower class limit. So if you take any 2 consecutive class limits, 61.5 minus 59.5, you get a class width of 2. And if you do the same thing up here, 75.5 minus 73.5, you also get a class width of 2. This 2 is the same class width that would exist in the corresponding frequency distribution table. The height of each box corresponds to either the frequency or relative frequency in a corresponding frequency distribution table. So here, this is the relative frequency of the fourth box, and it is 40%, the fourth class. So the histogram here shows heights in inches to the nearest half inch of 100 male semi-professional soccer players. So that's what this data represents. The most frequent heights are between 65.5 and 67.5. 40% of the sample have heights in this range. And we know that because we can see the relative frequency is 0.4 here. The least frequent heights are the tallest players over here. They have heights between 73.5 and 75.5 inches, and only 1% of the sample, and we know that because the relative frequency is 0.01, only 1% of the sample have heights in this range. The graph is mostly symmetrical. We talked about shape last time. Mostly symmetrical, you're going to see the bulk of the data in the center, and you'll see it trail off on the left and the right. This is mostly symmetrical because there's some odd stuff going on right here with this dip. But for the most part, we see the bulk of the data in the center, and we do see things decreasing on the left and the right. Okay, let's build a histogram on the TI-84 now. We are going to take note of the class boundaries from our frequency distribution table. We're going to take note of the smallest class boundary in the first class and the largest class boundary in the last class. This is going to make up the horizontal axis. So backing up one, okay, here the smallest class boundary is 59.5 and the largest is 75.5, and the horizontal axis is labeled in that range. We're going to do it similar here. This is going to be our horizontal axis range. It's going to go from 99.5 to 199.5. So we're going to take note of that, and then we are going to go to the calculator and fill in some values to make sure we can get this to look the way we need it to look. So I'm going to run through the slide first, and then I'm going to jump over to the calculator and enter these numbers in. So our data is already in L1, so that's the first step. You have to have your data listed in the calculator. And when we view it as a histogram, we could examine its shape, and we can quickly understand how the data is distributed and identify trends, whether most patients fall into a specific blood pressure range or if certain ranges are underrepresented. So viewing it as a graph is a very quick and visual way to make determinations. Before viewing the histogram, retrieve the lowest class boundary, the highest class boundary, and the calculated class width. So we know the lowest class boundary is 99.5. The upper class boundary, highest class boundary is 199.5. And let's not forget the class width, 20. We're going to be using all of that on our calculator. Okay, so we're going to press a key on our calculator called window, and it's going to bring up a screen that looks like this. We're going to enter the minimum x. So this is the horizontal axis that we're defining here. The minimum x is going to be the smallest class boundary, and the maximum x is going to be the largest class boundary. X scale is going to be the class width. Y min, sometimes I make this -5, but it really isn't necessary. If you want, you could make this 0. It's just the bottom of the graph. The -5 sometimes gives space, extra space at the bottom, but on the newer calculators, that's not so much an issue. Y max equals 16 corresponds to just a little above the highest frequency. Since the highest frequency was 15, I made this 16 so that our bars don't get chopped off when we view the graph. If you make it 17, it's fine. Just don't make it smaller than 15. 14 would chop off the top of the bar. Y scale and X res can stay at 1. And I'm going to go and put that in the calculator now. Okay, so here I am back at the calculator. If you want to get out of any location on your calculator, like this screen right here, the quit button is above mode. If you do second and then quit, it brings you back to the home screen. So I'm going to press and clear would clear out your home screen. Pressing window, you can enter some of the numbers that I referred to before. The lowest class boundary, 99.5. The highest class boundary, 199.5. X scale, 20. That's your class width. Y min, you can make this -5 or 0. If you make it -5, here's your negative key. It's different than the minus sign. So the minus key. Negative key is down here to the left of enter. Okay, but if you're okay, you can make this 0 and that would be fine. Just 0. Y max, like I had said, just a little more than the largest class frequency. Y scale and X res can stay at 1, and these deltas and trace step can stay the way they are. Okay, so next, after we've got the window set, we're going to turn on the particular graph we want to view. This calculator is capable of viewing several different graphs. So what we're going to do is press the stat plot key, use the second function, and then stat plot, which is along the top. I'm going to demonstrate it in a moment. If any of the plots are set to on, like notice that these all say off. If any of them say on, let's all start on the same page and select number 4 and hit enter and turn everything off. So let's start together and then we'll turn on the first one together. So we're going to highlight number 1 and press enter, turn it on. When you hit enter, you have the option of turning it on. So you're going to hover over or put your cursor on, and then press enter. Then you're going to go down to type, put your cursor using the down arrow to type, and choose the picture of the histogram and select enter. Then use your down arrow again, go down to X list and make sure that this says L1 or wherever your data is, and then frequency stays as 1. Okay, and now I'm going to do that on the calculator. Okay, so let me quit the screen that I'm in right now. Second quit, and I'm going to go into this blue stat plot function. So second stat plot, and mine are all off. I'm going to put my mouse on the first, not mouse, my cursor on the first one and hit enter. Going into the first plot. Number 1, or plot number 1 is currently off, so hovering over hovering over on, I'm going to press enter. Okay, going down to type, I'm going to go over to the histogram picture using my arrow to the right and press enter. X list, I'm going to specify second L1. And I do have the option on this calculator of changing the color. I'm going to leave it at black. And I'm going to quit this screen now. Second quit. Okay. I pressed the graph key. If I did this right, if I set my window numbers correctly and I did my second stat plot settings correctly, when I press the graph key, I'm presented with a picture of a histogram, and you should see this too. If you press trace to the left of the graph key, you see details about this histogram at the bottom of the screen. The flashing cursor tells you that you're on the first class, and at the bottom of the screen it says that the minimum is 99.5 and the maximum is 119.5. That matches the class boundaries from our frequency distribution table. This n equals 7 is the frequency of this first class. Now, in the first lecture, I explained that n is the size of the sample. So don't confuse 7 with 50 because 50 is the true size of the sample. Here, 7 is just being used to indicate the size of this first class. If I use my arrow to the right, I see the second class now, and at the bottom of the screen, I see my class boundaries, 119.5 and 139.5, and I see the sample size I see the frequency of that class 15, and keep going, and it should match exactly. So you can use your frequency distribution table as a check on the histogram and vice versa to ensure that these details match up, the boundaries and the frequencies. Okay, so the way we got to that graph, after setting stat plot settings and window settings, we press the graph key, and this is what, similar to what we saw. It's slightly different because it was a different calculator model I used here. But the idea is you do see the lower and upper class limits, flat boundaries, and the frequency. Okay. Um, the shape of this graph is slightly skewed to the right. If you remember from the other lecture on shape, a skewed right distribution has a longer tail on the right side, and we call that skewed right. Okay, the longer tail on the right side indicates that you have some data on the right-hand side of all the data values. So on the upper side, that's dragging or pulling the graph out to the right. So most of the data values are on the left. Some data values are trailing off and decreasing in frequency on the right, and that is what skewed right looks like. So let's analyze this. The histogram can be a useful statistical analysis of blood pressures. You can track interventions over time. You can track interventions over time by comparing the frequency distribution of blood pressure before and after lifestyle intervention strategies. For example, promoting diet and exercise to reduce the prevalence of hypertension. You can use it to compare outcomes in clinical trials. For example, how many patients' blood pressure levels decreased after medication. So here's a comparison of two histograms. Imagine what we created was before medical intervention, and maybe we did some kind of intervention and then took more data results and graphed those. And this is what our histogram appeared to look like after medical intervention. So maybe our intervention was implementing lifestyle changes. The graph on the right, 6 months later, after 6 months, appears to be even more skewed to the right. Remember, this one was slightly skewed right, but this one is even more skewed right, which is good because in blood pressure, high data values, which occur on the right side, this is high blood pressure up here. These high values, if this is a deeply skewed right curve, it means that we have very, very few people with high blood pressure. Whereas over here, being slightly skewed, we have more people with high blood pressure. Here it's more infrequent. So that would indicate that the intervention was successful. We're going to end with a histogram problem where we are analyzing this completed histogram. So we see that we have sodium content in snacks. So we have a set of snacks in our sample, and we measured the sodium content in these snacks, and the sodium content were measured here. These are the class boundaries that indicate sodium levels, and the frequency would be the number of snacks with a particular sodium count? Okay, so let's answer a couple of questions here. What does this histogram tell us about the third class? So let's start labeling from left to right the classes. We have the first class is the first bar, the second class is the second bar, the third class is the third bar. What is the histogram telling us about that third class? Well, it looks to be it's the highest frequency. So let's verbalize what it shows us. There are 16, because that's the frequency of that class. This vertical axis is not in percentage. This is just the straight number. This is just the frequency. 16 snacks with a sodium content between, now the third class has a low limit of 199.5 and a high limit of 249.5 milligrams of sodium. How many snacks were there in the sample? Well, I can see that there's 16 in just the third class, but that's not the entire sample. Looking at every class, I can see I have 11 in the first class and 10 in the second class, 16 in the third class, 6 in the fourth class, 5 in the fifth class, and 2 in the sixth class. So if those are the frequencies for each of the classes, I know that I can calculate the entire sample by adding up all those frequencies. Adding them all up, I have a total frequency of 50, and that is the size of the sample. The relative frequency of the fourth class. So fourth class right here, let me outline it. So this is the fourth class with the 6 on top. That is its frequency. That is not its relative frequency. To calculate the relative frequency of the fourth class, we have to decide what is 6 in terms of a percent. So we are going to convert frequency divided by total and times 100. That means we're going to take 6 over 50, 6 divided by 50, and multiply it by 100. That's 0.12 times 100, and that gives us 12%. So the relative frequency of the fourth class is 12%. And I think that's the last, yes, that is the last question. So that concludes the lecture on histograms and frequency distribution tables. That should give you enough of a introduction to these topics so you can complete the homeworks successfully. Next, we are going to be talking about mean, median, and mode and measures of variability. So I hope you're sticking with the material and learning the calculator little by little, and I will see you at the next lecture.